Most users treat large language models like conversational search engines. They assume the model will intuitively interpret nuance and intent without explicit structural guidance, often resulting in high-variance, unpredictable text. This approach relies on inputting free-form conversational text, similar to texting a colleague, while expecting a highly precise, expert-level response in return. This diagram of a text node web illustrates the blend effect. Without explicit structural constraints, a transformer's attention mechanism defaults to the statistical average of its training data. As the model leans into high-frequency tokens, the output becomes generic, weighed down by buzzwords and inconsistent formatting. To achieve professional utility, the conversational approach must be abandoned. LLMs are non-deterministic compute engines. Prompts function as structural control architectures designed to govern token probability distribution. Achieving predictable, production-grade output requires applying rigid systems engineering to the model interface. This structural diagram illustrates a four-tier architecture, beginning with Layer 1, System Context and Operational Boundaries. System Context provides a mechanical restriction that limits the model's parametric search space, preserving compute power for high-level reasoning. By establishing an epistemological baseline, like assigning the explicit domain of a growth architect, a bounding box snaps around a knowledge cluster, locking out irrelevant parameters. Explicit tone constraints further refine this space. Mandating an objective tone removes conversational variance. A strict knowledge baseline prevents the model from generating redundant information. If the reader is defined as a senior developer, the model will not allocate tokens to explain basic Python syntax. Standard prompts frequently lack these limits, leaving the context window open to high-frequency, generic data. Establishing firm operational boundaries forces the model to ignore generic token paths, increasing the baseline quality of the output. Layer 2 adds negative constraints, shifting the focus to boundaries of exclusion. Language models favor high-frequency conversational tokens by default. Forcing higher-value token selection requires the active suppression of these linguistic tendencies. A word blacklist acts as a laser grid, destroying specific buzzwords before they are generated. Format exclusion removes conversational filler and polite introductions. This leaves only the dense core data required for the task. This layer also enforces structural boundaries, such as specific sentence lengths and the mandatory use of the active voice. While a naive prompt produces text riddled with filler, a constrained model generates clinical, precise data. Defining negative space leaves the model no choice but to utilize more specific, high-value vocabulary. Layer 3 introduces decoupled reasoning, an architectural solution to structural logic failures. Large language models encounter a token prediction bottleneck when asked to compute complex logic and format output simultaneously. Mechanically, models generate the next word without the ability to plan the complete logical sequence in advance. We resolve this by forcing the model to allocate compute tokens to an intermediate thought process before drafting the final answer. Hidden XML tags isolate this compute. Within this buffer, the model evaluates the request through a multi-step decision tree. First, identify core constraints. Second, map a technical solution. Third, validate against negative constraints. By writing these steps into the context window, the attention mechanism evaluates its logic before committing to the response. Decoupled reasoning replaces flat, single-pass text generation with multi-pass logical validation. This transforms the model into a methodical analytical engine by providing dedicated processing time. The structure is completed by Layer 4, Output Schematics, which governs the delivery format. For analytical tasks, avoid unstructured, open-ended paragraphs. Professional outputs must be deterministic and machine-readable to be immediately useful in technical pipelines. Mandating strict data structures like JSON schema, Markdown tables, or YAML forces the output into a predictable array. Defining a schema forces tokens into a strict spatial architecture. Each data point slots into a predefined category. The complete architecture ensures a highly professional payload that executes exactly as designed. Schematics act as the final physical constraint, ensuring raw compute is packaged into zero-edit utility. Bringing all four layers together shows the systemic prompt architecture in simultaneous execution. This architecture treats the model as a precise compiler of natural language, significantly reducing output variance. Static templates lack these underlying operational constraints, which leads to inconsistent results across different sessions. This architecture targets the underlying token probability mechanics utilized by transformer models. Applying these layers shifts the technical focus toward designing logic flows rather than drafting conversational queries. In enterprise environments, this methodology prioritizes predictable pipelines over the high variance of standard prompting. This systemic approach should be integrated into all daily operational workflows with AI tools. Stop chatting with models, start programming them.